All right, so we are going to talk about a bunch of stuff today, but before we do that, you have Carolyn and Jonathan, two both seniors who are, you should aspire to be as smart as these two. They're both doing amazing things here, and then beyond they will also do amazing things. But they're going to talk to you about the Computer Science Exchange Night, which is happening tonight. Unfortunately, it has also the time we're going to have a review session, but I'm going to tape the review session, so prefer to go to their thing than ours, and you'll be able to watch ours later. Go.
Yeah, so like he said, that was a very kind introduction. We're here at the Computer Science Exchange, and we've been having a series of project and ideas night over at Tamper Cafe at 7:30. And this one that we're having tonight is geared more towards 11 and 15 students to really practice developing project ideas and then pitching them. So if you have an idea that you've been thinking about for an app that you think would be cool, or just a problem that you want to have solved, you can bring that. Or if you just want to practice pitching an idea, really rapidly prototyping something, meeting a ton of new people, we'll have ideas there. It's going to be a really fun event. There's always free food. There's going to be a raffle for big tech prizes.
Furthermore, there will also be delicious swag offered by Facebook, so you should come to that. And also come if you have any questions about Facebook. I am Facebook's campus ambassador for Tufts. You can ask me questions. Shameless, what questions we should hold for? So we have some free swag.
Ooh. Take it.
Oh.
See, you get a benefit for sitting in the front row here.
Yeah.
And by the way, you're not allowed to pitch a Boggle solver to these guys tonight.
Yeah, we really, there's going to be a lot of upperclassmen, hopefully a lot of other students in 11 and 15 for you to get to know. It's been a really fun environment so far, so we hope to see you there.
All right, thanks. See you guys later. All right. So let's do this. Let's go back to where we left off the other day. We're going to do a lot on this thing called Dijkstra's algorithm today. Now remember, last week we started with, or on Monday we started with graphs. And graphs are like the Wild West of data structures. No real structure to them. They've got vertices and edges, and everybody can connect to everybody else. And you've got all these different possibilities. And one thing that we definitely want to do, especially if we're doing like Google Maps, right, is the shortest path algorithms. And we stopped the other day by kind of going through a shortest path algorithm for unweighted graphs, right? Well, what happens if we all of a sudden have weighted graphs? Well, there's this thing called Dijkstra's algorithm. There's actually a number of algorithms. There's this famous one called Dijkstra's algorithm. And Dijkstra was a famous computer scientist, one of the giants in computer science. He's the first one to solve this. He actually solved it, but not in the most efficient ways, it turns out. Go figure. But he solved this problem for the first time. And he's also a guy who has IJK straight in his name, and we use those letters a lot, so I kind of like him too for that. But anyway, we're going to talk about this, how to solve this algorithm a little bit. Then we'll stop and we'll talk Boggle for a few minutes. And then a couple, like maybe a Unix tip of the day or something. Then we'll go back to Dijkstra again. So I don't want it to be all Dijkstra all day. But we are going to talk about this a fair amount today. OK? Any questions before we get going? All right, we're going to practice these things too. This is another. Remember how I said quicksort was like the big first algorithm? You guys had to like kind of the big first algorithm we learned. This Dijkstra's is kind of the second one. And more people have probably heard of Dijkstra's algorithm than quicksort, believe it or not. All right. Dijkstra's algorithm does shortest paths from some node to all the other nodes, right, for weighted graphs. So we now have numbers on the graphs which say it costs this amount to get from node one vertex to the other. Okay? It's what we call a greedy algorithm. Okay, we've actually dealt with greedy algorithms before. Hint, hint, you might want to use one for Boggle. You don't have to. It's a possibility. But a greedy algorithm solves a problem in stages by kind of saying, this sounds like the best thing to do. Right? It says, I'm going to go this direction because it sounds like a good way to do it. And then it keeps going in that same direction. It doesn't come back until it gets to some dead end, is what the algorithm really ends up doing. Okay? Greedy algorithms are interesting. You will hear more about greedy algorithms as you get through more computer science classes. But it turns out greedy algorithms don't always work. Before we even tell you exactly what they do, let me show you a greedy algorithm that works and then how we can change it so it doesn't work, and you'll kind of get a feel for that. OK? All right. This is actually a question that probably 15 years, 20 years ago, more people would be able to say yes. But have you ever had to count change out in like a retail job? Have you ever worked a retail job and they've had to count change at all? Yeah. So most of the time the computer does it for you, right? But what if the computer's wrong? Or what if I do this all the time and I screw like cashiers up all the time? They're like, OK, it's 5.43, and I give them like 2 pennies, and that like their mind gets blown, right? Because they're like, I can't figure out the I just don't want the extra pennies, right? But making changes is, if you are going to make change so that you give out the fewest number of coins, this is actually a greedy algorithm. OK, so let's say you had to give out 15 cents of change. OK, now in American money we have quarters, dimes, nickels, pennies, right? Or $half if you want. But we can limit it to these for now. First, you count the biggest ones. Then you count the next biggest ones. Then you count the next biggest ones to give out the fewest number of coins. OK, and that kind of makes intuitive sense, right? You want to give people the biggest change you can back. All right. If you want to give out 15 cents change, right? Well, what are you going to do? You're going to go, here's a dime, and here's a nickel, right? There's no quarters, because you can't give out, because that's more than 15 cents already. You give out a dime, you give out a nickel, you're done. 2 coins, right? OK, that works. You can trust me on this, that it works for American money, it works for every possibility that you would want. All right? You just start counting from the top and you go down. We can change that, however. OK, let's say we added a 12-piece. I don't know what you'd call a 12-piece. Anybody know? Anybody like make up a 12-piece name? I called it a does or something. That would be kind of good. A doubloon, is that a 12? It's a something else in some other currency. I know that. I call it a 12er. I don't know. But let's say you were to make 15 cents change with having a 12-cent coin, which would be ridiculous, by the way, having a 12-cent coin. But maybe, I don't know, maybe. You would do it this way, right? You would say, OK, I can't use quarters anymore, but first I'll use a 12er. And then I've gone past like the ability to use a nickel. So now I have to use 3 pennies, and all of a sudden I end up with 4 pieces of change, right? When what could I have done? Right? You could have just used a dime and a nickel just like before if you were trying to make 15 cents change. All right? I'm seeing some confused faces. Right? The 2 coins is still available if you have a 10, or 25, 12, 10, and 5. But if you do the greedy method, which says just start going down and picking the biggest one to get myself there the fastest, you will not use as many. You'll actually use more coins. OK, so these greedy algorithms kind of work that way. They start at kind of the big problem. They say, what's the best thing I can do right now? Go that way. What's the best thing I can do right now? Go that way. OK, see how that works? OK, that's the greedy algorithm that we're gonna do, and it doesn't always work. The good news is it happens to work for Dijkstra's algorithm, which is good. But just be careful if you're trying to figure out a greedy algorithm. You might have to figure out whether it's going to work before you actually do some calculations with it. OK. So Dijkstra's algorithm goes in stages, just like the unweighted one. Remember how we had the unweighted graph, and you start at a vertex, and then you kind of go to its adjacent ones, then you go to their adjacent ones, et cetera. It's a stage-based one, just like the previous one that we talked about the other day. And here's how it actually works. OK? Select a vertex. Right? We're going to select one of those. OK? And then you select a vertex which has the smallest distance among the unknown vertices. Now, let's say that we're going to start at 1. Even if there's 4 and 5 going here, how far does it, or how much cost is it to go from v3 to v3? 0, right? So you're still going to say it's 0 there. But then of the ones that are unsolved yet, you're going to pick the one with the least path. This is the greedy part. You're going to say, I think by going down this path, I'm going to get to where I'm going faster. Doesn't always necessarily mean that will be the final answer. But for solving the result, which again is trying to find the shortest path from one point to the other, you're going to pick the next shortest one to go to. You'll see how this works in a bit. Okay? At every stage, the algorithm actually decides whether or not you're going to use a weight on a particular path, whether it's a good idea by this greedy method. Okay? All right, so here's how it works. Okay? We are going to start at vertex 1. That's going to be our start right there. Okay? And we're going to start at vertex 1, and we're going to mark the distance as 0 because it doesn't take any distance to go from 0. And we're trying to find the shortest path from 1 to everybody. Okay? Here's what we're going to have in the table this time. We're still going to have all the vertices. We're going to have whether or not they are already known or not. In other words, don't go back to those ones. They are already known. Okay? And then we're going to set up, same thing as before, we set up everybody that's unknown right now has an infinite distance so far. Right? We don't have any idea how far it is starting out. I mean, it's obviously in whatever table we're keeping this in, but it's not like we don't know how far from us it is yet, or from the start point is. Okay? And then we're also going to keep another path here, or another variable here, which tells the one that it came from. In other words, if you update one of these distances, and let's say you were updating 7 from 4, you would change 7, and then you would say the previous one that I came from was v4. This will allow us to trace the actual path a little bit later. Okay, so this is what we're going to do. Okay, everybody get the idea here? Trying to find the shortest path from one place to the other. We're going to practice it later on paper, and we're going to do that. Okay? All right. So let's take a look at this. So we checked vertex 1, and we mark it as known because it's 0 distance. And then we adjust v2 and v4 because those are the only two that are adjacent to v1. All right. Well, how much cost is it to get to v2? Well, it's 2. So you mark down 2, and you put, hey, I just came from vertex 1. So far, so good? Same thing with vertex 4. You're going to mark it as being 1 away from 1. And you're going to mark saying, I just came from vertex 1. Okay? Then we can now go on to the next ones, but we have to make a choice here. Okay? We have to make a choice because we've now we've got 2 going over here and 4 over here, right? Actually, before I even go to the next thing here, we have to make a choice which one we're going to do next. You always choose, of the unknown ones, you choose the one with the fewest, or the shortest distance already. That's the greedy part. Okay, so which ones are unknown? 2 through 7. Which one has the shortest path right now? 4. That's the one you have to deal with next. So far, so good? Okay, so you do that. And you'd say 4 does what? Well, 4 is adjacent to a ton of things in this graph, right? 4 is adjacent to 3. It's adjacent to 5, 7, and 6. And we can then say, OK, if we look at vertex 3, well, first of all right, so we look at 3 and we say, how far is it to get to 3 from the amount that's already at 4? It's 2 more. So you update 3 to be 3 now. That make sense? Okay, and then you do the same thing for the other ones, right? To get to v5, you're going to have 1 plus 2, so 3 is at 5. And by the way, we mark where we came from. And then the same thing with 7. We go to it's going to be 5 total to 7, and then we mark it as coming from v4. And same thing with 6. It's going to be 9 total from 6 and v4, and then we're good. And then we mark v4 as now being solved, okay, or known in this case. All right, which one do we have to do next? Which one? Maybe you guys don't get what's going on here. We have done this, right? Which one?
I was just going to say v3, but my question is, would we have to go back?
We haven't dealt with v2 yet. Is it solved yet? No, we haven't even touched v2. We've only touched v2 to update it. We have not used it to go to its adjacent ones yet, right? So you the nice thing about keeping this table is, OK, it's right there. You say which ones are not solved, right? Which ones are not solved? All of these, well, all of them except like 2, 3, 5, 6, and 7. Which one is the least right now? That's the greedy one you have to do next. OK, so the greedy one we have to do next is v2, and so we have to take care of that one. v2 is adjacent to 2 and 4. I'm sorry, adjacent to 5 and 4. Right? So we have to do those ones. All right. Well, we're not going to update the 2 to 4, because 4, first of all, is already known. And even if we updated it, you're not going to go, v2 right now is 2. You're not going to add 3 more and change the distance of 4. You're just not going to. Yeah?
How do you know that v4 is now solved?
We've actually marked it as being solved in the first column right here. It's now known. We just did it, by the way. But this is the column you have to care about, right? The known column. All right? We'll see. Trust me, you'll practice this, and you'll go, oh, okay, I get it. This is not a particularly hard one. It's an interesting one, but not a really hard one once you get done with it. OK, so we don't even bother changing or checking v4 because it's already done. But we do have to adjust. We can check 5, right? To go from 2 to 5 would be an extra 10. So it would be 12 more on there. But we're not going to make 5 12 because it's already 3, and you're not going to update something with a greater distance. The whole point is to find the shortest distance. OK? All right. So now we're going to set 2 to true, or to known. All right. OK, of 3, 5, 6, and 7, which one do we do next? Or there's a choice. 3 or 5. This is where you get a choice. There are some choices in this algorithm, right? You can do either one next. Turns out it will always work. Oops. OK, you can choose either 3 or 5. All right, we'll do 3 just for kicks. Right? If we do 3, same deal again. 3 now, it's adjacent to, let's see, 3 is adjacent to 1 and 6. OK, so to get to 1, well, 1 is already solved, so we're not going to bother with that. And it would be 0. It wouldn't update from the 0 anyway. And then the 6, so 5 plus whatever's at v3 is 8. And do we want to update it? It's not going to change. Or sorry, it is going to change. It was before. What was it before? Yeah, it was 9. Sorry, it was already 9, so we are going to update it to 8. OK? All right, we mark mark 3 as known. And then you see how this is working now? This isn't so bad, right? And then now we have to pick 5, because of the remaining unknown ones, that's the shortest, right? And so we go to 5, and we say, OK, to 7 would add 6 more from what's on 5. That would be too big. So that would be 9. We're not going to change that one. And that's the only one it's adjacent to. So it's actually not going to change anything. All right, and then you have to choose 7, because it's the next the unknown of the shortest distance. Right? 7 is adjacent to both 6, or to just 6. So we're going to need to update 6. Let's see. 7 is 5 right now. Right? Come on, pointer. Not working. 7 is 5 right now, and it's going to go up by 1, which would make it 6 to v6. It's 8. So do we change this one to 6? Yeah, because we want it shorter. We change to 6. And then we mark that one as known. And then the last one is 5, or the last one to do is 6 now. And 6 happens to not be adjacent to anybody anyway, so nothing's going to change. OK? All right. And that's it. And that's how we've done this algorithm. And now, if you'll notice, all these distances here are the shortest path to get there. The question is, how do you figure out from this table what the shortest path was? We know what the number is, but how do you figure out what it was? Yeah, back in the back. Yeah. Yep, in the red. Yep.
We look at also like if like you're going to 6, you look at where it came from, and then you see where that one came from, and keep going back.
Yeah. Let's do 6. That's a good one. So we want to go v1 to v6 in this case, right? So we start at v1, right? But we can't start there to actually figure it out. We have to start backward. We have to start at v6 and go backwards, right? So what goes to v6? v7 is where it came from, right? OK, where did v7 come from? v4. Where did v4 come from? v1, and there you go. And if you add them up, hopefully that'll be the right numbers here. Let's see. 1 plus 4 is 5, plus 1 is 6, and v6 is 6. So you see how you can figure that out? Using going backwards on the thing there. So this is actually a pretty neat algorithm, all things considered. Right? It will figure out the least path. Whenever your Google Maps is trying to find stuff, it uses something similar to this, if not this exact algorithm. There are other searching algorithms to find a shortest path. It does have to deal with all the nodes, right? You can't just say, I want to go to 5, figure out what the shortest distance to 5 is. When you've solved 5, you can stop, right? If you know you've gotten there and it is the least, you can definitely stop. But until that point, you might not be, you would have to keep going. But that's the algorithm in a nutshell. Okay? And we'll practice that in a little bit. Printing out the graph, nice recursive algorithm. Basically, you print the path. Basically, you go through the, if the base condition is if you're not a vertex, right? And then you print the path from that path, and you just print out the vertex, and that will actually go backwards and it'll go 6, 7, 4, 1, and that's the path to get there. Okay? Yes?
Does this only help for finding the shortest path from V1? Can you kind of figure out the shortest path from V1?
Yeah, that's a good question. Would you have to redo this if you wanted to go shortest path from somewhere else? You kind of would, right? For lots of reasons. Reason number one is that you might not even be able, you can get to V6 from V1, but you get from V1 to V6, but you can't get from V6 to anybody, right? So there's no like inverse sort of thing to this. And it also just has to do with the fact that you've made assumptions about, look, it's going to be 0 to start out with. So you can't really redo this. You have to go from each little point you want to. Yeah. Well, so I don't know exactly how Google Maps does it, but they do this iteratively a number of times. Yeah, yeah. And we'll talk about the asymptotic complexity and how hard that is too. But I mean, think about it. If Google Maps is going to say, go from here to Seattle, right? You could drive from here to Seattle by staying on Route 90 the entire way. Now, Google Maps probably wouldn't necessarily do that, but they'd get pretty close. Right? They might route you into Canada or something. I don't know, but they would route you. So they might change some things, but more or less they'd probably go around the big cities. But otherwise, you could stay on that. So once they find a pretty short path, they've narrowed it down a lot, right? If you're going from if this was New York, and I mean if you were doing New York to Seattle or Boston to Seattle, right? Well, you only need to do that once for the whole thing, right? But then you say, oh, no, I really want to stop in Chicago. Oh, reroute, and it'll do here to Chicago, and then redo it from Chicago to there. Yeah, that's the way I'm guessing how they do it. But they've had a while to think about it too. Been doing mapping things like this for a while. Good. Other questions on this? All right. It's not so bad. So that was what we were supposed to get through yesterday. Let us stop for a minute and shake out the Dijkstras. We'll come back to it in a few minutes and try it. But here's what I want to do. Couple tips of the day. I've been kind of holding off on one because we had too much other stuff to do, but I think we've got time today to do a couple things here. And then we'll do Dijkstra's algorithm again. In the meantime, oops, I skipped it in here. We got to talk a little bit more about Boggle. Okay, and I will answer any more questions today and then talk about a little review session tonight that sadly overlaps with that. Let's do that right now. So I told you I would do a review session. Turns out I would have rather done it tomorrow night, but I have to be out of town to Seattle, of course, for the Navy. And we're going to do it tonight. Halligan 102 is the room I've got. It's not a huge room, so if all of a sudden like 95 people come, we might have to think something else up. But as far as if you want to come to the review session because you don't really get what's going on with Boggle, by all means, I will tape it. So it's going to be, I'm going to videotape it, and it'll be basically, these are the kind of things that I've been toying with, and I'll firm it up a little bit, but kind of a free flow, and you guys can direct it if you want. But I thought we'd talk about, like, how do you get set up? Just like knock that out right at the beginning. If you haven't set up your Eclipse or whatever, just let's get that going so everybody's on the same page, or Kate, or whatever you want. And then we'll talk about some actual algorithm ideas. This could be the most important if you're like, I have no idea how to solve this. Maybe we'll talk about some strategies. Okay, I won't actually code them because I want you guys to be able to code them. But if you have no idea what the strategy might be, then we'll talk about that. Using the dictionary class. We'll talk about all the functions in there. How are we going to test our code? This is the one that's a little tricky. I put some Piazza posts. As I'm figuring more about this project, I'm putting Piazza posts out there. Bruce wrote this, and we had to I've been trying to figure out some various ways of getting through his code, which is very well written, but it's deep. There's a lot to it. The back end sort of stuff. And then, how do you handle the QUs? That's a weird special case in this whole Boggle board, right? It's definitely the wacky one. Okay? And then I will show you also how to show the same board. If you saw the Piazza post about that yesterday, I tested it again today. I need to amend that a little bit, so I will do that I will change that Piazza post. But you can if you want to test it using the same board on the website each time, there's a way to set it up to do that. Okay? So we'll talk all about those things. What other questions you guys have at this point about Boggle? Yeah, Kate.
Reading in from a file, does this use like if string?
No, you can use cin to do all of it. If you want to use ifstream, you're welcome to set it up. I'm not opposed to it, but I think cin works just fine because here's how the dictionary of the list of words is going to be given to you, right? You're going to have word 1, word 2, word 3, all the way down to word like 170,000 or however many words there are. And then you're going to have a period on a line by itself. The way I've set it up, I guess I could just change it. I probably should just change the word list to actually have the period in there, but it might screw the actual website up. So I'd rather not do that. But what it's going to be is a bunch of words and then this. So basically you have your cin statement says while whatever your word is not a period, keep going. Right? OK, so good. But that's what we can talk more about that tonight if you want as well. Other questions on Boggle? Yeah?
Do we have to, when we publish, do we publish once or multiple times?
When you publish, you have to publish every time you make. And that's a very good point. Thank you for bringing it up. I was testing mine the other night and kept getting and changed things, and nothing was changing on the screen. And I forgot. If you do the make in your directory, you have to type /publish, right? And that will actually push your files, the executable files, to your web directory. And then you can do it on the website. So thanks for bringing that up. You have to do that every single time. So don't forget that, or you'll go crazy wondering why it's not working. Or you can test it on the command line. And I will show you how to do that. It's probably easier to test on the command line because you can make up your own dictionary and you can make up your own Boggle boards and whatever. But if you want, you're going to eventually want to test it on the website as well. Other questions? Nothing else? You guys are doing great on it? OK. Show of hands. How many people think they might show up tonight? OK. Might be a little crowded, but we'll figure it out. Bring a laptop if you got one. Be able to set that up. OK. Let's see. That is enough on Boggle. Couple Unix tips of the day. Now, I promised you this one a while ago. And this is actually, I think, an interesting one. Remember we talked about sed briefly, which was the stream editor. And you could bring something in, and it would find the words and maybe change them for you if you want in a file. It would like change, find and replace, basically. The way it works is this thing called regular expressions, which is actually really neat. Regular expressions, also known as regexes, or I guess that's how I pronounce it. I don't know how other people would pronounce it. But basically a sequence of characters that form some pattern that you're searching for. OK? And you have these wild cards, and you have special characters, and so forth. But the way it works, and by the way, you will see this again when you get into theory of computation. You guys spend like a ton of time, not a ton of time, like 2 days or a day or whatever on this stuff. But like you dig into the details of it. The most basic regular expression is just a single character. So if I want to match A in a particular string, right? If I want to match all of the A's in this string, it will say the apple was eaten, and it matches all the A's. That's easy. OK? You can also match multiple letters. And the way regular expressions work is they have these special like characters. You say if you put 2 letters inside a bracket, you actually say that will search for either of those. OK, it'll search for the E and the A, but then this E as well and that A to search for either one. So it's like an OR operation. It's kind of cool, right? If you wanted to put an actual bracket, search for that, you'd have to put like a backslash bracket to say, nope, this is not a special character. Okay? You can also match ranges, which is neat. If you want to match all A through M, it will give you all the letters that are A through M. It's kind of cool. Okay? And it knows that A, B comes after A, et cetera. Okay? You can also do these wildcards, and this is where it starts to get a little bit crazy, right? If you put a period, that will match any character. That says a period says any character, whatever. Okay? So if you do A period period, it will match A followed by any character followed by any character, right? So it's APP matches, and AS space actually matches, and ATE matches. Okay? It was hard for me to get the color on the space. Couldn't do red on that one. A star matches 0 or more of the previous character. Right? So if I said P star, that would only match P or PP or PPP or PPPP, etc. It matches any repeated 0 or more times of the previous character. So P star matches the PP here and the P here. Gets a little bit more interesting, right? A dot star says A followed by any character and repeated any number of times, and any character is any character repeated. So any character here, any character here. It doesn't have to be the same character in a row, right? So this actually matches all of the rest of this because it's any character repeated any number of times. Okay? You can also say, hey, I want the beginning and the end, which would be like the beginning is the, by the way, anybody use Vim? A couple people I know use Vim. I've talked to you. If you use Vim, you'll notice some of these characters are similar. Vim uses regular expressions a lot. You can actually check for the beginning and the end if you're not in insert mode by hitting the caret to go to the beginning and $ to go to the end. But that's just the characters for the beginning and end. So if you match caret THE, it only matches, well, it actually matches the entire, well, I guess I should not have had this one. That probably shouldn't be done. If you're doing the whole line, it will match that. If you do caret apple, well, because the apple part does not come at the beginning of the line, it's a no match. Okay? And then D period $ says anything with a D and then any other character, period counts, it's a wildcard, to the end of the line. Okay? That's how these regular expressions work, which is pretty cool because you can use them to find interesting patterns. And you can make up lots of interesting ways to do your searches. For instance, let's say if you want to do a special character, you can do \period, right? And that would do that. If you did poison / character, the apple was poisoned yesterday, well, there's no period there because it's a special character, right? And this one would just be a wildcard match. You can actually test these things at these various regular expression tester places. Like, let's go to one. Let's go to regexpal and try something here. Okay? If we do a regular expression, like let's say we want to look for ABC, and we type something that says the letters in order are A, B, C, D, E, F, G. Can you notice that it highlighted the ABC there because that was our regular expression, right? We could also do, let's say we did dot would find both ARE and ABC. See how that works? So you can test these and figure out where these things are. What if we wanted to just match at the end of the word? Let's say, well, let's do ABCDS. We'll call it like that. So we just want to match at the end of the word. Whoops. GS, we'll call it. Then we would have to do something like S. Notice S by itself gets that letter and that letter. S with the $ on it only gets this one because it's the end of the word. So you see how these things work? They're actually, like, really, there's whole books written on regular expressions and how to use them. So I just wanted to show you a little bit about these because you'll see them again in later courses, and you'll have to practice them a little bit, or you'll have to know kind of how to use them. Yeah, no.
So if you're searching for A or like whatever, for example, do you need to specify if it's uppercase or lowercase?
There's a special, you know what, I don't know what it is, but there's a way to say either upper or lowercase. Yep, there's a character you put before it that says, don't worry about case. Or you can search for the whole string and say, don't worry about case. Yeah. Other questions on regular expressions? They are pretty neat when you use them. And they're used in all sorts of programs. The grep program, which searches through files, uses them. Sed, we already talked about, uses them. And Perl and JavaScript, they all have regular expressions kind of built right in. So you'll see them a lot when you start doing other programming in other languages. Okay? All right, last thing on the tip of the day. This is another one just to show you the words.dat list of words for your Boggle assignment. It's like 170,000 words long, so it's a pretty big file. It's not a trivial sized file. What we've done is we've made what's called a soft link. And then when you do setup for Boggle, it does this for you. It puts this link here and says, it links that folder to in your directory. And now you can just type cd data or data/words.txt, and you get access to it. You can't write to it. You can read from it only. So you can't update, you can't change the file, but you can read from it when it's a symbolic link like this. Well, with the permissions you've got. Okay, that's all that does. And so if you see that like it's colored crazily, then you'll notice when you do it at ls, you'll notice it. Yeah. So it's done for you when you do setup. When you set up the Boggle, it will do it for you. So I just wanted to show you that it's there, and you can do that. And if you wonder how we made it so that everybody gets the same copy of the words, in your public HTML file, you've also got links to the originals of all the website files. So in case we find some mistake, we can update one, and everybody gets the change immediately. So that's kind of nice. Okay? It also means if I screw up and change one and break it, all of yours will break. So that would be bad. Yeah?
We did this when we did the picture editing lab, right?
Yes, we did the same thing with the picture editing for the images. Yes.
So when you when you go in, how do you get back out?
You have to actually. It depends what shell you're in, believe it or not. But I think you have to use CD to the actual directory that you were in before. You have to use the whole name. Yeah. You could actually do CD and then tilde is your username or your path, and then I don't know, desktop /comp15 /HW9 or whatever, or 6 or whatever, right? So you can't just go backtrack. It goes back into the original, I believe. I tried that the other day. Depending on the shell, I think, but it does make a difference. Yeah. OK, anybody else? All right. So let's go back to Dijkstra's algorithm. And this is where you guys are going to actually try it out. So here's what I'm going to do. I've got a bunch of pieces of paper, so you don't have to write these graphs down. In fact, I'll give you about half. You guys know how to send pieces of paper around the room efficiently? Just pass one to everybody near you. Right? Because if you pass one to everyone near you, you've already got one, just pass them on, and then they will get through the group really fast. Right? Just pass them to everybody. Don't worry about being. Don't worry about if you've already got it, just pass it again and grab another one and do it. It's the fastest way to get papers through the classroom. I will wait until you get those passed out. Did you rip one, Maya? If there's extras, just leave them on the ground in the back, and I'll pick them up at the end. Or leave them on one of the desks or something. OK. Who's missing them still? You guys back there? Pass them over to these guys, too. Thank you. OK. You guys have them in the back? You guys have enough? How many more do you need? Who doesn't have one? One? There's no extras? Did I really pass out exactly enough except for one? That's kind of amazing. I'll bring them back. I feel like Rain Man. Really? Everybody else got one, huh? And there are no extras. That was amazing. All right. Oh, two more. Oh, all right. So here's what we're going to do. So on the paper, you've got two sides of the paper, like every piece of paper. And go to the side that says perform Dijkstra from vertex 1. That's the side you want to start on. Because we're going to do this for both of them. OK? And I am actually going to let you guys go for a little bit. OK? And I will write up the board. I'll do it up here and start filling it in myself. Much like always, when you're doing this stuff on the board, you can make mistakes. So correct me if you see me make a mistake. But for now, I'll tell you what, I'll start you out for now, right? Vertex 1 is already solved. You can write that one, or you can check that one as known. OK? You can say that it's already known. And you've now got to go from vertex 1 to all adjacent vertices. And this is the graph we're doing, this kind of big-looking graph up here. OK? It actually is kind of a big-looking graph. But if you start at 1, notice that there's 3 places that you have to update, 6, 7, and 2. Right? And you just update those on here based on 6, 7, and 2. And don't forget to update previous, too. OK? So let me draw it up here. You guys will start. I'll draw it, and then we'll get there. Yes. There you are. Okay, if you have no idea what's going on, I did the first one for you here. Like that. Starting at vertex 1, the only things that change are 2, 6, and 7. Right? And they change to 2010 and 25, and you have to mark where they previously came from. Okay? All right. Don't forget to update your previous's. All right. Hopefully I didn't make too much of a mistake here. Oh no, I don't have the actual response up there. Okay, so hopefully you guys can see the answer here. I did post the answer online too. Keep going if you want. Don't mean to stop you. Keep going if you want. But if you want to look at the answers here, if you find a mistake I made, let me know. And if you don't get it, I'd be happy to help you. Did you find a mistake, or do you think I?
No, I just don't get it.
Which one?
Well, like, I don't really understand how you close the public then.
How to do which one?
Like any of them, really.
Okay, so you've done this one first, right? Okay, so the next thing you do is you say of the unsolved ones,
Yeah.
which is the least.
This one.
So that's the one you're going to do next.
V6.
V6, yep, good. And so put 10 there because you know it's not going to change.
Okay.
And then what does V6 go to?
5.
Okay, and 4 and 3. So you got to check that. So 6 to 5, you have to add 30 to it. So 6 to 5, so 30. And they all infinity, so it's whatever that is. So 6 plus 5 is 30, so that's going to be 40. All right. And then 6 plus to 4 is how much?
4 is 25.
So 20. So 10 plus 25 is 35. You see how it works now? And then 6 to 3 is 20. Yep. Yeah, good. And then the other ones are all going to be the same because they don't change because you can't get to them. So 0 and 20 and 25.
And then you look for the smallest
And the
one.
smallest one there. Yeah, of the unsolved ones. You've now solved this one, so you probably want to cross that out and put solved.
This one.
Yeah. See how that works?
Sort of. Yeah.
Okay. If you get done, you can. Did I screw something up? Which one? Here? Okay, so let's see. How did I get to 3? This, you agree with this?
No, I think that's what it should be.
So you agree with this?
Yes.
Okay, so this one's okay. So let's see if I did this. So we agree up to here. Okay, so, and then at this point we have solved 6 and 1. So we can't look at 6 and 1. But of the rest, 2, 3, 4, 5, 7. 2 is 20. 3 is 30, 4 is 35, 5 is 40, and 7 is 23. So this is the one we want to do next. Did I do that? No, then we did, V2 is the one we want to do next. Oh, sorry. You said you agreed with this one? Okay, we've already done 2. So you're right. So we've got to do, so 2 is solved, and 6 and 1. So 3, 35, 40, and 23. So 23 is the one I do next. You get that? That makes sense. So that's V7. Okay, so V7 connects to who? I left my paper somewhere. V7, 3 and 6. So we might have to update those. So V7, we may have to update this one and this one. All the others can stay the same because nothing's going to change for them. 23 is 23, 40 is 40, 35, 35, 20, 20, 0, 0. So what would make it update to 23 to 3, 7 to 3 is add 2. 23 plus 2 is 25 less than 30. Yes, so I update 25, and I have to say that this comes from V7 now. Okay? And then how about V6? Well, V6 is already solved, so we don't care about changing it either. Yeah, Zoe? So 23 is what V7 started at. Yeah. 20. So we're working on vertex 7. So if you're working on vertex 7, what does vertex 7 connect to? 3 and 6, correct? It's adjacent to 3 and 6. So if it's adjacent to 3, let's look at 3 first. How much more is it from 7 to 3? 2 more. 23 plus 2 gives you 25. Is 25 less than what 3 started at? Because 7 was already at 23. Remember, you were building this up in pieces, right? At this stage, at this point, we know that the shortest distance from 1 to 0 is 1 is 0, 2 is 20, 3 is 30, etc. That's the shortest path so far. We need to now start at the next shortest one and see which one's shorter from there. Jenny?
Should V6 to V3 be 20 instead of 30?
Let's see. Which one are we on here? Here?
Yeah, V6 to V3.
OK, V6. Does it go to 3? It does go to 3, and 6 plus 20, it's 10 plus 20 gives you 30. Okay. Yeah, this algorithm takes a little bit of time to like click, right? And again, I might have made more mistakes, so catch me if you think I made a mistake. Yeah. Chris or Andrew. Say again. Yeah. Let's start from this perspective right here. Let's say that this is the situation right here where 2, 6, and 1 have already been completed. So everybody else needs to be taken care of, right? Or need to go to that. So of these ones, which one is the shortest of the ones that aren't 1, 2, or 6? So skip 1, skip 2. 30 is less than 35, 30 is less than 40, skip this one. 23 is now less than 30. So this is the one we have to deal with at this point, the 23. Once we're dealing with the 23, we go, OK, 7 is the one we're going from because it's vertex 7. So where does vertex 7 adjacent to? Vertex 7 is adjacent to both 6 and 3 because it's got arrows going out of them from 6 to 3. So you look at 3 and you go, OK, how far is it from 7 to 3? Or 7 to 3 is how much more? 2 more. So 23 plus 2 is 25. So the shortest distance at this point to vertex 3 is 25. And guess what? 25 is less than what it's currently at v3, so you update it to 25. Yeah, you're adding it to the one you're coming from. The table might be confusing people. If you look at the graph and try to think, hey, maybe if you did it on the graph and updated the graph ones, maybe that might help. I'm not sure. You have to get used to it. Yeah, Tim.
I think something that might help is once you turn something into true, you can just write that value
all the way across. Yeah.
all lines so that you can see that that's sort of.
Yeah, that's a very good point. If you've marked one as true, is it ever going to change? There's no way it can become less, right? So you can just go whoop and mark it all the way across. That's much better. That's a good way to do it. Yeah, absolutely. Yeah, Zach. You mark it as true when you're looking at its vertices, or sorry, its edges, its adjacent edges. And you say, so if we started on this column V7, you would say, OK, now you can do it right at the beginning or the end, it doesn't matter. But now, after we do this, 7 is now solved. Because it can't be any less because it was already the least, and there's no way to get fewer numbers. Like you can't go down, at least with positive numbers here. OK? All right. I won't make you do this now, but you do have a from vertex 4 on the back of this one. If you have done it already, great. If you don't, please do it like at your leisure so you practice this. I can almost 100% guarantee, right, that I will give you a question like this on the final exam. Question, come here. When you get stuck, yeah, I mean, if there's no adjacent vertices, it won't change, won't update anybody. You mark it as done, and we're gone. In this case, I think the only one here that does that is maybe 5. But it turns out we look at 5 last anyway, as it turns out. But for the one in the back. Yeah, I mean, same thing. If you get to 5 and have to deal with 5 early, yep, you just leave it. You just say it's marked done, and there's no adjacent, so you didn't update anybody. OK? Yeah. To find out what the next vertex is, what if there is no next lowest distance? You mean if they're ties? If there's well, infinite would count as the next lowest, but yeah, I mean you wouldn't be able to update anything because infinity plus infinity would never update anything. Yeah, you'd be done, basically, because you can't get there from here, right? I mean that's kind of at that point you're like, oh, you're right, I never can get there. Right? So if we tried to start this and we said, find the shortest path from 5, right? We'd go, OK, 5 is 0, and then everybody else is infinity, but there's no way to update anybody. And then you'd be done with that, and then everybody would be infinity, and you go, oh, I guess I'm done. Right? The main effect. OK? All right. Any other questions on this? If you need to practice this, or if you didn't get this, come to office hours. We'll work on it. Or look up things online. I want you do need to know this algorithm and know how to kind of manipulate these things. And if I didn't do a good job up here, let me know and we'll figure out a different path. All right? OK. All right, let's move on to a couple other things. Dijkstra's algorithm will always work if there's no negative cost edges. And this actually gets kind of, in some sense, a little like mind-blowing, right? First of all, we'll look at how does this perform. Then we'll think what happens if there are negative cost edges. So every single time we're trying to update this, don't we have to look through all the vertices to see which one is the least? So that's going to like make things a little bit hard to do, because if you have to do that, for every vertex you have to look through all the other vertexes or vertices, what kind of performance is that? Squared performance, right? N squared or V squared. It's proportional to the square of the number of vertices. That's the actual answer that Dijkstra came up with, believe it or not. OK, he came up with that. Right? So you've got to go through all of these guys. Right? That's the obvious algorithm to do this, but it's V squared. Right? The number of vertices. What if this was all the vertices? Right? I did my best. You should see how hard it is to make a graph where it's totally, completely connected. It's not easy, because you got to remember every single one. And there's a ton in there, right? There's for 5 different things, there's 25 different arrows I had to write there. It's a pain, right? And both, actually, I had to do 50, I think, because both ways, right? So yeah, there can't be 50 in there. 25 maybe? I don't know. But it's a lot, right? It's a lot of, yeah, 25. 5 for each one gets 5, so 25. But it's that would not be a good graph. Most, did I get them all? Don't even say if I didn't get them all. That's just mean. I tried to make it completely connected. But if you do this, this would be a very dense graph and not a particularly fun way to do this. And in fact, if you were talking cities, right? Well, actually, cities is a bad example, because one city probably doesn't have one road that goes to all the other cities. It's just steps. So most graphs are not dense like this. Most are actually relatively sparse. Remember, we already talked about an adjacency matrix is not a particularly good way to store these things, because they're sparse, right? If the graph is sparse, right, it's just too slow. It doesn't make sense to do this V squared algorithm. Turns out there's a better way to do this. And this is not one that Dijkstra came up with. Even though he's got a super brain, he didn't come up with it. Right? What we can do is we can use some data structure we've used before that you might not have thought about. We can use a priority queue or a heap, right? Which is basically a priority queue. Every time you change a distance, you insert the vertex into the heap, do all the heap properties to make it a heap, continue it as a heap, and then select the next vertex. Because isn't that really what we're doing? Is we're selecting the vertex with the shortest distance? And if we put it into a heap, won't everything bubble correctly so that the top one in the heap is the minimum one? Like, that's the whole point of a priority queue or a heap. So that's what we're going to use. So it's really cool. The people who came up with this, I think, are like super brilliant, because they do this. I won't do that. I don't know that I'll ever do this, but I've always wanted to write like a history of data structures. Like, I want to know who came up with that. Like, what was that guy thinking, or gal, or whoever it was? What were they thinking that there's like to use a heap for there? They must have taken a data structures class, right? So let's do this. So let's check out what would happen with that. OK? Here's what we're going to do. I'm just going to walk through this one with the heaps here. Here's your beginning heap. Put on the vertex that you start with. Throw it on the heap. And then we're going to basically get remove min and deal with that one, right? So you do delete min, or I guess delete min. Delete min removes v1, right? And when we remove it, we say, I'm dealing with it. It is now known. OK? So I'm dealing with v1, and it's now known. And you adjust v2 and v4. They go onto the heap, right? Those vertices now go onto the heap, and whatever their minimums are. And so we know that 4 was 1 and 2 was 2, so a distance of 2. So the heap ends up looking like this. You take this one off and then put these two on, and guess what the min is? 4. No need to search through these anymore. You've already taken care of it with your priority queue. It's beautiful. It's brilliant. Right? Now you take 4 off, and you say, I now know you, because you are now known because I'm about to deal with it. So 4 is now known. And then we say, what's 4 adjacent to? It's adjacent to 7. It's adjacent to a bunch of things, 5, 7, 6, and 3. Right? And they all have to be updated and then go into the heap. So update them and make them go into the heap, right? After you do this, the 3 and the 5 and the 6, the 3 and the 5 are kind of tied, but that's okay with heaps. In this case, it's fine with heaps. It doesn't matter which one you deal with next. Whatever it ends up bubbling up is fine, right? And your heap would have to be able to deal with that, but that's it. Okay, so then we do one of those. We remove min here, and the 2 now gets removed, and we deal with 2. Okay, and 2 is adjacent to, let's see, 5 and 4. Now, you don't update 4, so if you did update it, you would put it back in the queue. And by the way, vertices can end up in the queue more than once, but by the time you get known, if they're already known and still in the queue, we're done. Don't need to worry about them. Okay, so then we still got the queue. Now we're going to deal with whichever one happens to be. It happens to be 3. So we do 3, and we take it out, and we say 3 is adjacent to, 3 is adjacent now to, let's see, 6 and 1. We're not going to update 1, but we are going to update 6. Because as it turns out, 6 had been less than 8, remember, or more than 8. Remember it was 9? I'll go back one. This happened to be 9. 6 was 9. And then when we're dealing with 3, which is now 3 plus 5 is 8. So we have to update 6 to 8. Well, we throw 6 back on the heap. Well, there's 2 6s on the heap. Who cares? Whichever one we get to first. By the way, which one are we going to get to first? The one with the 9 or the one with the 8? Remember what our heaps do. Our heaps take the next one in order. So even though 6 is way down here in the heap, it's going to climb up and go out before this poor 6 is going to. Right? So you're going to get the right one, as it turns out. And so this 6 is going to bubble up there. But the next one, of course, is 5. And you deal with 5. And 5 comes out. And you have to update both 6. 5 actually, actually 5 is now, you just update 7. So 7 comes, and you don't actually update it because it's already less than it would be otherwise. So now we're down to dealing with 7. Okay, we deal with 7. And 7 goes to 6, which is already, it's not going to go, oh, it is going to go down. We actually have to put another 6 in there because 6 went from 8 to now, let's see, 7 to 6, right? So it's going to be in there. So now I get all these 6s in here. But which one comes out first? The one that's the 6 because it's a heap. And it's brilliant, right? So you deal with 6. 6 happens to not be adjacent to anybody, so it comes out. Then you pull the other 2 out. You pull 6 out, and you go, well, I've already dealt with it. So it doesn't need to be done. It doesn't need to do anything, and then we're done. So this is much faster than searching through the whole list every time. Much faster. OK? Questions on that? Did I go too fast on that? Yeah.
Are you done when your heap's empty?
Done when your heap's empty. Much like a lot of these things we do, right? A lot of times we said, while the queue's not empty, or while the stack's not empty. Same thing, right? For Boggle, it's going to be basically the same idea, right? While the board is not completely solved, keep solving the board, right? If you're doing it recursively. Or if you're doing it with a stack or something, you know, or a queue, or however you decide to do it, you can, same idea. Yeah. Other questions on this? I think this is a brilliant way to handle this problem, right? Asymptotically now, well, turns out, so what do we have to do here? We have to look at, for each edge, right? We have to look at each edge. And for each edge, you have to perform a delete min. And the delete min part is log of the number of vertices, right? Log of the number of vertices. So what we've got is for each edge, you do a log of the number of vertices. So basically, the overall complexity is the number of edges times the log of the number of vertices, which beats n squared. Think sorting. N log n beats n squared. Just like in this case, E log v beats v squared. OK? Much better. Yeah, Jeremy?
So if you have like an extremely connected graph,
Mm-hmm.
something that first would like n squared log n. Or no, wait, it would be first n log n rather.
It would be the same sort of thing. It'd be n log n in that case. Yeah, I mean,
If everything was connected to further vertices,
yeah. Well, let's see. How many? It depends. So if everything was connected, you would have n squared vertices, right? Or n squared edges, or whatever, v squared edges, right? So you'd have e squared log v, yeah. You'd have e squared log v. But that beats e squared squared, right? I mean, your v squared beats that too. So this is a better way to think about that. OK. All right. Now, this is the kind of the interesting case. And I'm going to let you guys think about this for a minute. What if we did have negative costs, right? The whole point of Dijkstra's algorithm is, hey, I'm going to be greedy here, and I'm going to mark things as known when I've seen them, because you can't go backwards and get a shorter distance. If you've got a non-negative path, if it costs me 5 to go to you, and then I'm trying to go to anybody else and back to you, you will never be less than 5 if everybody else is positive. Does that make sense? This idea that you can't go down if you have positive costs. If you have negative costs, all of a sudden you can go down. You can't say, hey, I know that you're completed now, because somewhere along the line you might backtrack and go negative. And then all bets are off, right? So you've got to be a little more careful about that. Is there an easy solution to this? I want you to think about this to your neighbor. So here's the deal. We have this like this, and the problem is we've got a negative 40 in there. What's one way we could maybe deal with this? Think about it for 2 minutes, 3 minutes. Does anybody have any ideas? Yeah, what do you think, Josh? Yeah, what if you did this? What if you added 40 to everything? What if we made it 41 to make it positive? So there's no zeros in there at all. What if you just added 41 to every one of them? Would that work? Now you've only got positives in there. Does that work? What do you think?
I don't think it would work, because you wouldn't do that before.
Well, you wouldn't be able to go down, right? Okay, so that's true. You wouldn't, but why? So, but expand on that a little bit. Okay, what do you think? Yeah, go ahead.
The nominal difference is the same, but the relationship.
Well, even the nominal difference kind of is the same, but keep going on that. I'm going to press you guys a little bit more. Yeah. Oh, sorry, Kate. Right back and then go. Go ahead.
Well, if you were talking about how you'd be like stuck in an infinite loop,
Uh-huh.
that would be like the only issue.
There's no infinite loops if we make everything positive, right? There's definably not. We know that Dijkstra will finish if we did Dijkstra on positive ones. That's guaranteed.
But then you're changing the cost.
Well, you are changing the cost, but does it affect you?
I would say, yeah.
Can you say why?
Well, because otherwise, if you didn't change the cost, you keep going.
Okay, so kind of intuitively you go, look, you can't change the problem here and like fix it by just doing that. But I want a little bit more deeper. Yeah, good. Okay.
Well, I feel like this might be what you were saying, but like if you left it at negative 40, you could continually make it less and less.
Yeah, you could, although by the way, there's no cycle here. I purposely changed some of these arrows so there's no cycle here, because you always end up at 6 and you can't go back from 6. So there is a way to finish this. This is also will produce the shortest path, but that's not really the issue. And then, yeah, go ahead.
Well, it'll change the
Yeah.
path that you're going to take. Instead of
Well, why will it change the path? This is what I want you guys to think of.
If you take the path from B5 to B4,
B5 to 4. Sorry, 5 to 4. Yep.
with this, if the negative 40 is there, it's going to be minus 34.
Well, but hold on. But Josh, weren't you going to say in yours, add 40 and then subtract all at the end? Subtract maybe 40s at the end? So you're subtracting it out at the end, right? So you just deal with it while you're dealing with it. Yeah.
But if you just subtract 40, then like it works for when you only have one jump, but if you go over 3 jumps, you've added 120.
That's the key. You guys going to say that too? OK, yeah, that's the key. So basically, what we were just saying was, yes, you'll add 40 to this, but if you add 40 to this and 40 to this, you've added 80 to a path of 2. And then if you only subtract 40 at the end, Well, that doesn't work out. The end result is you've doubled the amount of stuff you get out of it. So no, it doesn't quite work. Yeah. Could you do minus 41 times the number of edges? I believe that might work, although you might get stuck in the middle somewhere when you're still trying to do the algorithm. But yeah, I've thought of that too, and I'm not 100% sure that wouldn't work. Yeah? Well, this is how we're actually going to solve it. Yeah, you actually don't want to mark the vertex as known, as it turns out. What we kind of have to do, can't do this. This is the path where you do this, right? Dijkstra's, the paths with many edges become much more weighty, and that's the issue, right? So like that, there we go, much more weighty, right? So there isn't that a particularly easy solution. But yeah, if you say, OK, I can't deal with this, right? I can't say something's known, so I'm going to have to do more work. You can do that, right? What we're going to do is we're just going to combine the unweighted and the weighted algorithms here. We're going to do a little bit of both. OK? Forget about knowns. Can't use that anymore, right? OK, so the greedy algorithm isn't going to work. Remember I said sometimes it doesn't work? Well, this time it doesn't, right? But what we can do is we can use a queue here. OK? And the queue is going to basically say, look, at each stage, so put the first one on the queue, dequeue it, find all the edges such that we would change it, if we could, and throw everybody back in the queue. Now, this is going to be an expensive operation. Okay? For what it's worth, this is going to be expensive. We can't actually get much any better than n squared or v squared behavior, but it'll actually work. As long as there's no cost cycles, this will actually work for negative edges. Okay? Stick everything in a queue, and then just kind of every time you get to another edge you could change, throw it back in the queue, and repeat, 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 okay, until the queue is empty. If there are cost cycles, it turns out that you can do this with you can just say, I'm going to stop after a certain number. And as long as everybody's been visited like once, you can actually do it. OK? I don't think we have time to go through all these ones. But basically, this is exactly what I'm going to do. I won't actually skip you there. Cost cycles, if you stop after every vertex has been dequeued, at least the number of vertexes plus 1, you will be guaranteed to have a termination. OK? In other words, you'll be guaranteed to have a solution that will be worthwhile. OK? So, a couple last comments here. We've got 1 minute left. Where does Dijkstra's algorithm happen in the real world? Pretty much everywhere. Right? It happens lots of places. Right? We've already talked about things like Google Maps and such. Shipping. If you want to get your stuff shipped, you better find the shortest path to get there. Right? Otherwise, you'll lose money. If you want to route computer networks, if you, say, are chatting with somebody in Australia, right? Well, you don't want to have to go like the wrong direction around the world, right? Your computers want to find the shortest path. Telephone networking, which is basically a computer network, OK? Lots and lots of real-world places Dijkstra's comes out. Mapping, subway system, mazes, shortest paths. Look up shortest paths algorithms on mazes. It's really kind of cool. OK? There's also public railroad transport. People are still writing papers about this using Dijkstra's stuff, right? Using railroad trains and things, OK? So there's lots of places in the real world. All right. Any last questions? See you guys either tonight or next week.